All right, welcome to video lecture 10 for ECE 203. So last time we kind of took a first look at sampling, and this time we're going to essentially review what we saw last time and then also look at what happens to the spectrum of sampled signals. So how that helps us better understand aliasing, which is something we saw in the last lecture. Okay, so to remind everybody, sampling a signal is pretty straightforward, right? We're just going from this continuous time representation, this x of t, which is represented by the green line in this plot, to a discrete time representation, okay? And the way we do that is we input a sampling frequency, f sub s, and that is that tells us the rate at which we take samples in units of samples per second, okay? So the inverse of that is just the sampling period, this t sub s right here. Okay, so the discrete time signal is something. A discrete time signal is something that can be stored and processed on a computer. So that's kind of our motivation for sampling signals. And again, we look at this x of n, where n is in brackets, just to indicate that n takes on the values of the integers, right? So only integer values. All right, so that's the idea behind sampling. The second thing we looked at last time was reconstruction, right? And that's how we go from a discrete time or digital signal that can be stored and processed on a computer back to a continuous time signal. And that's a little more tricky, right? There's a little more freedom here to do different things. And the main question is, how do we connect the dots between sample points, right? Again, we have some t sub s, where that represents now this reconstruction rate, this reconstruction period. That's the amount of time we wait between consecutive dots when we recreate the continuous time signal. But there's the problem is that in between the sample points, it's not clear exactly how we should connect the dots. So we saw two quick ways we could do that. One was the staircase idea, right? Or the zero order hold, and that's where we simply just hold the value at the last sample point until we get the next sample, right? That's plotted in blue here. Okay, and the other idea was just linear interpolation. We can draw lines in between, straight lines between the different sample points. Okay, so another way that we could reconstruct the signal is something called ideal band-limited reconstruction. And the idea here is that we want to find the lowest frequency sinusoidal signals that somehow match the sampled data. And this is if you think about this, it's kind of intuitive thing to do. It's saying what's kind of the simplest representation, or the lowest frequency variations in between the sample points that still actually matches up with the data. All right, so when we talk about this, we're going to make this assumption that the sampled signal is from a sum of low frequency sinusoids. Okay, this can be made very general, but we won't really look at that in this class. Okay, so we're making the assumption x of t is this sum of n different sinusoids, and they have, one of them has a maximum frequency, which is just the note f max. Okay, so when we sample this, we get the usual expression for the discrete time signal, where we've just plugged in n equals ts into the continuous time signal. We replace t with n equals capital T sub s, right? And so what we're going to do is, now that we have some x of n, right? This is the sampled signal. We're going to say, we're going to ask the question, what is the simplest sinusoid, or simplest continuous time sinusoid, that matches those sampled points? Okay? And when we go through the examples in the rest of this lecture, we'll just, we can really just kind of manipulate the discrete time sinusoid and figure out what the lowest frequency discrete time sinusoid that matches the data, sum of discrete time sinusoids that match the data. Find the lowest frequency sinusoids that again match the data, and that'll give us what the continuous time reconstruction would be. So kind of again, the intuition here is that this band-limited assumption. So band-limited means that the frequency bands that are in the signal are limited, meaning they're low frequency. And this type of reconstruction makes sense because it kind of finds the simplest continuous time signal that matches the data xn. So the question we want to ask is, under what conditions can we take the signal x of n, the discrete time signal, and the sampling rate, and then somehow go back to x of t exactly? So we'll see a bunch of examples to better understand that. Before we actually go into any numerical examples where we kind of write things out and calculate things, I just kind of want to get this picture in people's minds of what's going on. So let's just say we were given the sampled points that are shown in the top plot here. Okay, so this is a discrete time signal, and we're given this, and if we were tasked with finding the lowest frequency single sinusoid that matched this data, we would draw the blue plot, the blue line that's shown in the second plot. Right? And this is actually, this is the correct answer. This is the lowest frequency sinusoid that matches the data. All right? And somehow we've sampled sufficiently fast here for this middle plot that we know that this is the unique representation of the lowest frequency sinusoid, right? It seems pretty clear that if you were to try and draw a lower frequency sinusoid through those points, it wouldn't actually work, right? But at the same time, there are also higher frequency sinusoids, right, that also pass through all of these sampled points that are shown in the first plot. And that's captured on the third plot below. If we take a higher frequency sinusoid, shown in red, it could be that sinusoid, and if it's chosen correctly, could also give us these sampled points. Okay? So band-limited reconstruction is just making this assumption that the data don't come from high-frequency sinusoids. Right? And again, we'll look at conditions under which that can actually happen. So let's actually see a numerical example. Let's look at sampling a sinusoid that has a number of sinusoidal components. Okay, so that's what I've written up here. And we just have, again, a continuous time signal x of t that's made up of a sum of different cosines at various frequencies f sub k, right? And they all have different amplitudes and different phases, right? So here's the frequency of each sinusoid, and each one has a different phase and a different amplitude. Okay, so we're just going to sample that at a rate of t sub s, at a sampling period of t sub s. So how do we do that? Well, remember this equation. We take x of n, that's just going to be equal to x of n times ts. So in the second term here, we've just plugged in everywhere we see t, we replace that with n times ts. And that's exactly what we did in this equation to the right? We just replaced t with n times ts. Okay, and then the next thing I want to do is I want to define what's called a discrete time frequency. Okay, and that's going to be denoted f hat. So f hat is just going to be given by f times ts. So f is the continuous time frequency, and ts is the sampling frequency. So we're just redefining something here, okay? And this is, again, discrete time frequency. Okay? So let's look at an actual concrete example where we just have two sinusoidal components. We're going to look at this a lot throughout this lecture just to get an understanding of what happens when we change the sampling rate. So let's say the signal x of t is just a cosine at 50 hertz, okay, this first term, minus 3 times another cosine, but at 150 hertz. Now let's say I decide I'm going to sample that at 100 samples per second, right? So that would mean TS should be 1 over 100, right? Let me write that over here, TS equals 1 over 100. Now I'm just going to plug in to this equation here, right? We can reuse that down here and come up with an expression for x of n. So now I've replaced everywhere that there's a t in this continuous time signal. I've replaced everything with an n divided by 100, right? Because TS is 1 over 100. So I get the following. I get 2 times cosine 2 pi times 0.5n, okay? And then minus 3 cosine 2 pi times 1.5n. So some of you guys might notice something a little fishy right away, but let's just do a little algebra and try and understand this better. Okay, so we can, of course, just copy. I'm copying this first term here into this next line. That stays the same. But now the second term I'm just expanding. I'm writing this 2 pi times 1.5n. I'm writing it as 2 pi times 1n plus 2 pi times 0.05n. Right, same thing. And so what you'll notice, just doing this little trick, all of a sudden this term that has the 2 pi times 1n, I can just cross that out, right? Because any integer value of n, remember n only takes on integer values, the cosine is the same. So we can just cross that guy out. So we're left with just this 2 pi times 0.5n. Okay. So now we have these, again, two terms. One is 2 cosine and then one is minus 3 cosine. And now they both look like they're at the same frequency. So right away you should be thinking there's something a little fishy going on. Something doesn't seem right. We started with a continuous time signal that had 2 distinct frequencies, and then we sampled it, and now we're somehow saying they're 2 cosines with the same frequency. Okay? So those I can of course just combine, and I get minus cosine 2 pi times 0.05n. So this is something happened here, and this is what's called aliasing. Okay? And what we did is we sampled too slowly. Our sampling frequency was not high enough. And when we did that, that actually caused the second term, this 3 cosine 2 pi was 150t, to actually alias. Okay? We'll see a plot of exactly what's happening on the next slide. But so then after we sampled it, it actually looks like it's at a different frequency. Okay? So the punchline here is we sample too slowly, so the discrete time signal x of n doesn't represent the original continuous time signal. And it's actually now impossible to get back to the original sinusoid without, of course, some side information. Okay, so how would we remedy that? Well, of course, the easiest thing to do would be increase the sampling rate. Okay? So we'll do exactly that. Let's increase it to 300 samples per second. And when we do that, we see, again, if we just plug back into that continuous time equation now, we end up with a discrete time sinusoid, x of n, that has 2 frequency components. One at a digital frequency of 1/6, and another one at a digital frequency of 0.5. Okay? And so here there was actually no aliasing. Right? We can write out the digital or the discrete time frequency. Okay? Discrete time frequency f hat, again, is simply the original frequency of the sinusoid times the sampling period, right? Which is 1 over 300. So that gives us 1/6. And the frequency of the second term is 150 for the continuous time signal. And again, TS was 1 over 300. So f2 hat is just 1/2. Okay, so both of these things are below 1/2, so that's a good sign. And if we were to check kind of the ratio of between 1/6 and 1/2, let's say 1/6 divided by 1/2, right, should give us 1/3. And if we were to look at the frequencies of the original sinusoids, they would also have a ratio of 1/3. So that kind of checks out intuitively. Things seem the same. Okay. So there's this kind of celebrated result or theorem, and that's called Nyquist's theorem, and something called the Nyquist rate. And what that says is to avoid aliasing, we have to sample at a sufficiently high rate. And that rate must be at least twice the highest frequency in the signal. So I just have that written here. So the sampling rate, in order to avoid aliasing, must be twice the highest frequency in x of t. And if we do this, it guarantees that we obtain at least 2 samples in every cycle of each sinusoidal component. okay? And that's kind of depicted in this picture here. This would be right at what's called the Nyquist rate. So the Nyquist rate is just twice the maximum frequency. And this guarantees now that we've taken 2 samples in every cycle of each sinusoid. Okay, so if in terms of digital frequency, that's saying that f hat must be less than 1/2, right? That's saying f hat, right, which is in units of cycles per sample, must be less than 1/2. Or in other words, the sampling rate must be big enough, so it must be greater than 2 samples per cycle. Okay. So what happens if we violate this Nyquist rate, this rate, if we actually sample slower than what we than the Nyquist sampling rate? Well, we saw an example of that on the last page, right? Let's look at another example. All right, and again, let's say, you know, we kind of know what the Nyquist rate should be here, right? The original signal, it's written up in the upper right-hand corner. The highest frequency component is 150 hertz, right? It's right there. So we need to sample at least twice that. Let's see what happens if we don't do that, and now we sample at 200 samples per second. This does another example. And we can kind of do the same trick that we did before, right? Again, we'll figure out what x of n is just by substituting an n times ts into this continuous time waveform. And then we get 2 terms again. The first term we'll just leave for now, but the second time we want term, we're going to play this kind of the same trick. And instead of writing 3/4, I'm going to rewrite 3/4 as 1 minus 1/4. Okay? And now I have 2 cosines. Cosine at a digital frequency of 1/4 and a cosine at a digital frequency of 1 minus 1/4. And now, you know, using that same trick, moving down to the next line, we can just kind of cross out this 2 pi n, right? Because cosine is 2 pi periodic, so any integer n that we put in, that's just going to give us the same thing. And then the next thing I'm going to do is we have this 2 pi minus 2 pi times 1/4 n. That's, of course, since the cosine of a negative angle is equal to the cosine of that angle, we can just get rid of the negative sign. Right? And so now, again, we're left with 2 terms, both at the same frequency. So something fishy happened, right? Something funky happened. And we're left with 2 cosines that are, again, at the same frequency. So this is, again, another thing called, another example of aliasing, right? And both of these examples we saw, we just kind of got lucky that the frequency in the sinusoids happened to be exactly the same after we played this trick, right? That's not the only thing that can happen. As another example, let's look at a sampling rate of 175 samples per second. Okay? So even a slower sampling rate. And we know there's still going to be aliasing, right? We're still violating Nyquist. Sampling rate would have to be above 300 to not violate Nyquist. And again, let's just try and do the same tricks we did before. Right? So we're plugging in the continuous time waveform just to get the expression for the discrete time waveform at a sampling rate of 175 samples per second. There's 2 terms. The first term is going to kind of leave that one alone again. The second term, we're going to split that up again until we're going to just write 6/7 as 1 minus 1/7. And then, of course, let's play the same trick. We can simply cancel out the 2 pi term, right? And then the negative sign, again, it's cosine, so we just can get rid of the negative sign inside the cosine argument. And then we're left with now 2 cosines at different frequencies. All right, so this kind of maybe looks a little promising, how somehow this feels a little better than before, but there's still this issue, right? When we look at these, the second term, this is now somehow at a lower frequency than the first term, right? Which doesn't seem right. The second term in the beginning was at a higher frequency. It was at 150 hertz, okay? The first term is still, you know, at a low frequency, but it's not, if we look at this ratio, right, between the frequency of the first term and the second term, there is it's not the same as the ratio of the original frequencies, okay? So to see that again, look at these digital frequencies. The first one, the first digital frequency is right here. It's 2/7 cycles per sample, right? And then that's written right there. And then also the second digital frequency now looks like it's at 1/7 cycle per sample, right? And if we look at the ratio of F2 hat to F1 hat, that should be the same as the ratio. So the ratio of F2 to 1 hat, or F2 hat to F1 hat, right, is 1/7 divided by 2/7, right? And that should just be equal to 1/2, right? And the original frequencies we saw, the ratio up there was F2 over F1. F2 was 150 and F1 was 50, right? So that's a ratio of 3. So something changed here, right? These ratios, if we don't alias, these ratios should be the same. All right. So what's going on here? Well, let's take a step back and let's look at the spectrum of sampled signals. And when we look at the spectrum of sampled signals, that'll give us a better idea of what's happening with this idea of aliasing. Okay. So again, now let's kind of restate Nyquist. Right? And that Nyquist theorem is that if Fs is greater than 2 times the maximum frequency of x, then we're okay. We won't have aliasing. So if indeed Fs is greater than 2 times that F max, then the maximum digital frequency, F hat max, will be less than 1/2 a cycle per sample. Okay? And that's where, again, now if we define F hat to be equal to the original frequency times Ts. Okay? So that's just a kind of another way of stating Nyquist's criteria. If this digital frequency is less than 1/2. So again, now when we sample at the Nyquist rate, then the maximum sampled or discrete time frequency in x of t is less than 1/2. Just restating that. So let's look at the Fourier series expansion of a signal x of t. So everybody remembers this nice equation for Fourier series expansion, right? We have these AKs, these are the Fourier series coefficients. And then the key thing is we have harmonics of the original frequency, of the fundamental frequency f naught, right? That's f naught times k. So k is an integer. And in this equation, normally we write this from minus infinity to infinity, right? Here we're just writing it from minus n to n. And so all that's doing is saying that there is some maximum frequency component, right? And what that maximum frequency component is just n times f naught. Right? Normally when that's infinity, we say that the frequencies, there are components that go on to infinity, but we're just kind of truncating that. So if this were the case, if we had a Fourier series representation of a signal x of t that had this property where the maximum frequency was n times f naught, then to avoid aliasing, we would just need the sampling rate, right, to be greater than 2 times f max, or 2 times n times f naught. So let's just say we go ahead and sample at that rate. Let's sample right at this so-called Nyquist rate, which is Fs equals 2 times n times f naught. Then again, we're just going to plug in using this equation to sample the continuous time signal, and we're going to replace every place we see a t, we're going to replace that with n times ts. Okay? But again here, ts is 1 over 2 n f naught, right? So I'm just going to get, the f naughts are going to cancel here, and I'll just be left with a k divided by 2n. All right. So remember this equation, kind of next page, and kind of written it back on top. And now if we look at this, we have we can see the digital frequencies, right? The digital frequencies, or the discrete time frequencies, are just written right here, k divided by 2n. So the digital frequencies in xn are, well, the first one's going to be, say, a plus or minus 1 over 2n, right? That's when k equals plus or minus 1, plus or minus 2 over 2n, that's when k equals 2, and so on, all the way out to, I realized I missed a plus and minus here, but we have plus and minus that, all the way out to plus and minus n minus 1 over 2n, and then, of course, plus and minus 1/2 when k equals n. Okay? So here the digital frequencies are indeed less than or equal to 1/2. Remember, we're sampling right at the Nyquist rate, so we should be okay. So now we can plot the digital, the spectrum of x of n. All right? And so we're going to write that as x of f hat. Usually denote this with a capital X, denote that we're looking at the spectrum. And so as an example, just with 5 components, we would just plot this in the same way that we did, we saw when we just plotted the continuous time spectrum, right? But now on the frequency axis, we're going to plot the digital frequency in units of cycles per sample, okay? And so these coefficients, A0, A1, A2, A3, A4, A5, those are really just the same as they were from the continuous time case, okay? And we have on the horizontal axis, now again we're plotting cycles per sample. And so I'm just going to take those from these equations up here and plot the corresponding coefficient. Right? So pretty straightforward, looks just the same as when we plotted the spectrum of the continuous time signal. Right? Except on the horizontal axis now we put the digital frequency in cycles per sample. So let's just compare that with the spectrum of x of t, the continuous time signal, and it looks the same, right? We just had we just relabeled the horizontal axis. Okay, nothing too difficult here. But one thing to note is that there was not any aliasing. If there's aliasing, things change. Something happens, and let's see what happens on the next page. All right. So let's go back to the simple example we had, the two sinusoids added together. And if we sample at fs equals 300 samples per second, we indeed get no aliasing. Right? And if we draw the spectrum, we're going to get 2 components, right? The first component is a digital frequency of 1/6, and the second one is digital frequency of 1/2. Okay, so f1 equals 1/6 cycles per sample, f2 equals 1/2, half a cycle per sample, and I would just plotting that just as I did on the last page. Again, on the horizontal axis, I'm plotting f hat, and then I'm plotting, of course, for the component that's at a 1/6, that has an amplitude of 2. Remember, using Euler's identity, we had to divide by a factor of 2 when we plotted the spectrum. So we get 2 over 2, so 1. That's these components here, right? And then we also get, the 2 other components now. Those have amplitude minus 3 over 2, right? Those are at a digital frequency of 1/2. So it looks exactly the same as the continuous time spectrum. If we were just to plot the continuous time spectrum of the original signal, the original continuous time signal, the axis would just be rescaled. Okay? So if we violate Nyquist, that's not the case. If we instead set the sampling frequency to be 175 samples per second, right? We worked that out a couple pages back. We get aliasing. And what happens when we have aliasing now, we have 2 of these components, right? Kind of rescaled the axis. The components corresponding to the higher frequencies have now been brought back in, and they're actually at a lower frequency. What happens if we lower the sampling rate? Well, we did this example a couple pages back. We had the sampling frequency at 175 samples per second. Okay, and the problem here, right, remember, is the second sinusoid actually looked like it was at a lower frequency than the first one. And then again, we can see that when we plot the spectrum. The second sinusoid, which has, should have an amplitude when we plot the spectrum -3/2, it's written right there, and right there, that actually now is at a lower frequency than the original, than the first sinusoid. Okay, so you can see that the spectrum does not look the same. That's because aliasing occurred. So aliasing does a number of things. It makes the continuous time, the discrete time signal then doesn't represent the original continuous time signal, and secondly, it screws up the spectrum. So we can no longer have the spectrum and then go back to the continuous time signal, right? Because we've somehow mixed up the frequencies and caused some problems. So you guys can imagine what would happen if we did this with, say, digital music or audio. If we undersampled, just setting the sampling rate too low, you'd have sinusoidal components that were at high frequencies, they'd end up at low frequencies, they'd be jumbled all over the place. Okay? So what's actually happening here? What happened on the last spectral plot that we saw? Well, it's actually easier if we just look at one sinusoidal signal. Okay? And we can just say, pick our favorite sinusoid, x of t equals cosine 2 pi f naught t. Right, so if we sample that at a sampling rate of fs, we get xn as written right here, right? And this, of course, is just f naught over fs is just the digital frequency. So we're just going to write that as f hat. And then in the next line, I'm going to play the same trick, the same game that we saw in the examples a few slides back. And that's just, I'm going to say, of course, f hat is equal to 1 minus the quantity 1 minus f hat, right? And then I'm just going to distribute n, that's that second line, and then the quantity 2 pi n, I can just cross that out, right? And then also the negative sign, it's cosine again, it's an even function, I can cross that out. So what do we conclude? We conclude that x of n is equal to the cosine 2 pi f hat n, but it's also equal to cosine of 2 pi 1 minus f hat n. Okay? So there's two different sinusoids, right? The seemingly different frequencies that give us all the data. Right? You can see that if this f hat is less than 1/2, then the lowest frequency sinusoidal signal, right, is just going to be given by this first term. If f hat is less than 1/2, then we're going to use that first sinusoidal signal. Okay? But if f hat is greater than 1/2, for example 3/4, then actually the second sinusoidal signal will be at a lower frequency. If we had 1 minus 3/4, that would give us a digital frequency of 1/4. Right? That's a lower frequency sinusoid. And so we'd actually kind of, if we were doing ideal reconstruction, we'd prefer that sinusoid on the right. All right, so what's going on with the spectrum here? Well, we can think of this picture that I have drawn below, and any time that f hat is less than 1/2, we're okay. Right? But as soon as f hat kind of moves out, and if it still hits 1/2, it's still okay. Right? But as soon as it comes below 1/2, well, let me erase this original guy. As soon as it goes above 1/2, it's going to somehow switch to preferring the sinusoid 1 minus f hat. Okay? So at 1/2 it comes out to there, and then you would think, well, I just keep increasing the digital frequencies beyond that, but that's not the case, right? Remember now this reconstruction, as soon as the digital frequency increased to greater than 1/2, our reconstruction actually just kind of preferred this, instead the sinusoid that was at frequency, 1 minus f hat, right? And the same thing kind of happens on the negative end. So what I'm drawing here, right, is if f hat is greater than 1/2, but let's just say for now it's less than 1, then we see that the spectrum, actually, we don't see the signal, we don't see the signal at frequency f hat, we see it at a frequency of 1 minus f hat. Okay? So this kind of drives home a bigger point, that the spectrum of digital signals is actually, we're going to say, is kind of only defined over the range of -1/2 to 1/2. And another way to think of that is that you can think of it as just kind of being repeating, this whole picture repeating. So we could define it to be greater than 1/2, and then we'd have the same picture would repeat from 1/2 to 1, and so on. And so this effect, right, this effect now, when we've sent frequency, a digital frequency of greater than 1/2, then it looks like a frequency at -1 minus f hat. That's referred to as aliasing. So that's what happens to the spectrum when we have